we are going to cover about what beta? Thermodynamic process. What do you mean by a thermodynamic process? Can anybody say? Yes, thermodynamic process. What do you mean by it? Thermodynamic process. Yes. Any idea about it? What do you mean by it? Just think about it and tell. Yes.
A process due to which state of a gas changes.
Yes, very simple, right? Any process that brings any change in state of a gas, right? The reason behind change in state of a gas is what? Nothing but thermodynamic process, right? So do you know any thermodynamic process from chemistry?
Isothermal, isobaric.
Isothermal, isobaric and adiabatic.
Is isochoric.
Isochoric. But that are all the subcases of a particular thermodynamic process. It's not like a different process you are saying. All processes are just the subcase of a general process.
Polytropic.
That is known as what? Polytropic process. Okay? So let's first discuss what do you mean by a polytropic process. Polytropic process. Okay. So the students who already has covered the lecture yesterday, those students please don't give answer. Okay? So now other students, please try to give answer. What do you mean by a polytropic process? Yes, or just?
P into V raised to n is constant.
Okay. But that is an equation, right? It's just like I am asking, so what do you mean by isothermal process? And you are saying, sir, P1 V1 is equal to P2 V2. So it's like that. So you are saying what, beta? Equation. And what I want? Definition of polytropic process. And what do you mean by it? What type of thermodynamic processes are there that we can call what? Polytropic process. That is what I am asking. Yes, tell me, beta. Yes, any student in the class? Chitransh? Okay, dear students, those thermodynamic process in which specific heat of gas is constant are known as what, beta? Polytropic process. No problem, beta. Yes. So those type of thermodynamic process in which what? Specific heat of gas remains constant. Sorry. In the first lecture only I said that specific heat of gas is a variable quantity. It can change depending upon state parameters, external conditions. But there are some process in which specific heat remains constant. Okay? So by common sense, I explained yesterday that what should be the specific heat of isothermal process. Do you remember it? What is specific heat of a isothermal process? Infinity. Because temperature is constant, heat required per mole to change temperature by 1 Kelvin is infinite. One more example I gave yesterday, that what is specific heat of an adiabatic process? Zero, right? The adiabatic process, heat exchange is 0, but still temperature is changing. So heat required to change temperature is 0, you can say, right? So by common sense, we can say that what will be the specific heat of some of the process, right? So if specific heat of any process is coming constant, it means that is what? A polytropic process. Okay, beta? And that specific heat will come out to be like, it can be anything. What I'm trying to say, it can be like 0, infinity, negative, positive, some number. Right, beta? Yes or no? Okay. Now, let's see that how to get that equation, how to find out specific heat, right? So what is polytropic process? Everything we'll discuss. Okay, if you apply first law of thermodynamics for any type of process, any type of general process, if you apply first law of thermodynamics, so you can write dq is equal to du plus p into dv. Yes or no? Can you write like this? Okay, dq, heat exchange, is equal to change in internal energy plus work done by gas, right? So, now what will be dq? dq I can write n c specific heat into dt. du what I can write? For every type of process, du has to be n cv dt. It's not like even only if volume is constant, then only we can write n cv dt. Always it is what beta? N cv dt. Change in internal energy n cv dt plus what beta? P dv. So P dv, yes, I will keep like that only. So n dt divide. So what I will get? C is equal to cv plus P into dv by dt. So what we got here? We got an expression, right? To find out specific heat of any kind of process, not just polytropic process. For any type of random process, if its equation you know, then you can find its specific heat by the use of this formula, right? You know my nature. I don't give any formula which has some exceptions. I don't like exceptions, right? So whatever the process is, right? So if once you know the equation, you know the polytropic equation or any general process equation, then just use this formula, you will get specific heat of that process, whether it is constant or variable, right? Now, okay, for example, let's say we have a process in which V is equal to 2T square. Somebody is saying volume is proportional to temperature.
Sir, P dV by N dt.
Yes, here it should be N also, right? You are right, beta. N. So dividing by N. So C is equal to Cv plus P dV by dt into N. Right, good. So suppose somebody is saying that V is equal to 2T square. That is the equation of a process. Find its specific heat. So what to do, beta? C is equal to Cv. Suppose that process is followed by a monatomic gas. A monatomic gas is following this process. What should be its specific heat, right? So we can use this formula. Right? Even that specific heat is coming constant, variable. That is a general formula. That I am writing from what? First law of thermodynamics. Okay. So C is equal to Cv plus P dV by dt and divide by N. So Cv, what is Cv for monatomic gas?
3R by 2.
3R by 2. Okay, beta. Plus P upon N. What will be dV by dt? 4T. Right? P by N into 4T. Now, if you have V is equal to 2T square, what you can write for pressure?
P is nRT by V.
Yes, P is nRT by V. Okay, so 3R by 2 plus P upon N into 4. Okay, and P, what we can write? What we can write, beta?
PV by
PV by?
NR.
Okay. PV upon N into R. Right? Listen, beta. So again I am explaining, like some students came late, okay? So for those students I am explaining again. So first what I have obtained, specific heat formula, a general formula, right? So that we can use for any kind of process. So C is equal to Cv plus P upon N dV by dt. That. Okay? Now I am giving one example that suppose a volume of a gas is changing by this equation, V is equal to 2T square, right? Then what will be specific heat of the process? Right, that is a question. Now what I am doing, C is equal to Cv plus what beta? This equation, P by N into dV by dt. So P by N into dV by dt I am writing. So it will be what? 4T. So how I can rearrange this term? So P I can write nRT by V, right? So T I am writing PV by nR like that. So depending upon what is required in the question, we can write specific heat in terms of temperature, in terms of pressure, in terms of volume like that. Okay? Understanding or not? Okay. So now let's come to polytropic process. So for polytropic process, what you know? That specific heat must remain constant. That is the definition. Okay? So that is this definition of a polytropic process. That specific heat must remain constant. Okay? Right. Now let's understand it. specific heat. Oh, thank you. Specific heat remains constant. Okay, beta. So that is the definition, right? So this term, the first term in the equation, must remain constant. Okay. Now let me rearrange this. Okay. C minus Cv is equal to P dV by dt n dt. Okay. Now P, what you can write, beta? N RT by V. Yes. C minus Cv n RT by V dV by dt into N. Okay. Now C minus Cv divided by R dt by T is equal to dV by V. Right, beta? So I am rearranging the terms like this. Now see, beta, this term C minus Cv upon R. I am doing this expression derivation for a polytropic process. Now C is a specific heat, a constant thing by definition. Cv, you know, is constant for a type of gas, monatomic, diatomic, a mixture, right? So you will have a particular value of Cv. R dt by T dV by V. Now integrate this expression both sides. Let's call this number, give it some name, right? Some constant. So let's say it is K, because every time I have to write this number, na? So it is K. ln T is equal to ln V plus some constant. Some constant, another constant, it's an integration constant. So say that is integration constant. Now let's bring this on the right side. I can write like this: ln V minus ln T upon K is equal to minus constant, right? So that term is constant only. ln V upon T by K is equal to constant, yes? Taking exponential both sides, constant raised to the power some, but exponential is constant only, right? So I can write V upon T to the power K is equal to another constant, say C1. Very constant only, no, beta, right? Okay. Now, but K is some number. This term C minus Cv by R, that is coming. So that I am writing as K. Now, beta, again, let's change T to what? P and V. So what I can write for T? PV, because NR will again go to the constant, right? So I can write V upon P to the power K, V to the power what? K is equal to another constant, say C2. Yes or no? You tell. Okay, now what I will write here? P to the power minus K, V to the power 1 minus K is equal to what? Constant, right? Okay. Now this also I can write P V to the power K minus 1 upon K. Please tell me if I am doing any mathematical error. Some constant there C2 I am writing. Let's write it C3. Some constant C4. No problem, right? So P V to the power K minus 1 upon K, right? So now K was some number, right? K is what, beta? Some number, some constant, and I am getting this kind of equation, right? So it means if specific heat of a gas is constant, you must get this kind of equation, and this complete thing I can write as PV to the power what, some x is equal to constant. So if specific heat of a gas is constant, then we must get this kind of equation. Or if any process is following this kind of equation, then a specific heat must be constant. In both ways, you can say. Understanding better? Yes or no? Right. Okay. So PV to the power constant. Now let's see what is this number? What is this x? X again is having a unique significance. So PV to the power x constant. Now what is this x? Let's say. Now x is equal to k minus 1 upon k. So taking that side, 1 minus 1 by k. So what I am getting, beta? 1 upon k is equal to 1 minus x, or x, or what, beta? K is equal to 1 upon 1 minus x. Yes or no? What was k? C minus CV by R. Yes or no? Okay. Dear students, now see 1 minus x, C is equal to CV plus R upon 1 minus x. So what I am getting? I am getting some kind of formula. So if I can express any polytropic equation, right, any thermodynamic process equation is given, PV to the power x is equal to constant, then directly I can get that constant specific heat of the process. I can get specific heat of the process. So C is equal to CV plus R upon 1 minus x. Very important formula. Right? Okay. For example, if I am saying PV square is equal to constant. So what is polytropic coefficient here? PV square is equal to constant. What is polytropic coefficient? So that is known as polytropic coefficient. Once you know the polytropic coefficient, you can find out specific heat very easily. So what is polytropic coefficient here in this expression?
3.
3. Not 2? No. First you need to rearrange the equation in this form. Power of P should be 1, and then the power of V is what? Polytropic coefficient. Right? Okay. So I can write T as what? PV. PV into V square is equal to constant. So what I am getting, beta? PV cube is equal to constant. So x is what, beta? 3. Yes. So beta, if you know the type of gas, suppose that process has been followed by a monatomic gas. So if you know the type of process, x is 3, so then 3 you can substitute here. What you will get, beta? Specific heat. So it's like this. Understanding or not? So specific heat directly you can find very easily for any kind of polytropic process. Understanding, beta? Yes or no? Okay. Now let's understand that why I am saying all the processes that you are saying are the subcases of polytropic process. What you said, beta? Isothermal process first you said, right? So now first you say isothermal. So for isothermal process, what is the equation? PV is equal to constant, right? Means what is polytropic coefficient here? 1. Means x is equal to 1. By common sense, what you said, what is the specific heat? Infinity. Yes or no? Now just put x is equal to 1 here. What you are getting, beta? Infinity. Getting or not? Okay. So that is isothermal. Number 2. What you said here? Isobaric. Isobaric process. For isobaric process, what is the equation?
V1 by T1 is V2 by T2.
Okay, means pressure is constant, right? So pressure is constant means P V to the power 0 is equal to constant, right? Like that only. Means what is x?
0.
You put x 0 here. So C is equal to CV plus R means Cp. So when pressure is constant, specific heat is what? Cp. Like that. Okay. So what else you said?
Isochoric.
Isochoric. Isochoric. So for isochoric, how to write this equation? Tell me.
P raised to 0, V is equal to constant.
Volume is constant, right? So in isochoric process, volume is a constant, right? Okay. So now, what to do, beta? So I want the P to the power 1 I want, na? So when power of P is 1, that time, what is the power of V? That is polytropic coefficient, right? So what to do? Like O just said, power 0, then V to the power something, this 1 is equal to constant. That is for isochoric process. But I cannot keep like this. Okay, what to do?
Infinity.
Raised to infinity, yes or no? So if I am writing here 1, so then I must write here what? Infinity. Yes or no? You tell. Is this correct? Yes?
Yes.
Okay, it means what is x?
Infinity.
No, x beta. Sorry. Now, yes, x is what beta? Infinity. Now put x equal to infinity here. C is equal to CV plus R upon infinity. 1 by infinity 0. Specific heat is what beta? CV. Like that. Okay. So number 4. What he said?
Adiabatic.
Adiabatic. So for adiabatic equation is what? PV to the power gamma. Right? So PV power gamma is equal to constant. Okay? So what is x beta?
Gamma.
X is gamma. You put x as gamma here. So what you will get?
CV plus R by 1.
Gamma is a Cp by Cv. Right? So that is minus R. Minus R. What you will get here? Minus Cv. So if you substitute x as gamma here, Cp by Cv, so this term what you will get? Cv minus Cv, so what you will get? 0. So for adiabatic process, you know specific heat is what? 0. Understood beta? So all the processes that we generally know are polytropic process. Understood or not? Okay? So any confusion is there, please tell me. Don't worry. So everything that I am writing here, I already sent you notes, okay? So no problem. Just focus on understanding part, right? So whether you are able to understand or not, just focus on that, okay? Yes or no? Yes. That we need to understand about polytropic process. What we already have covered, that what is the equation of polytropic process, PV to the power x is equal to constant, okay? So that you know. And now we need to understand what are the properties associated with it, right? Means what kind of questions can be found on the basis of polytropic process. Okay. So now dear students, number 1, very important. Slope on indicator diagram. Slope on indicator diagram. So what is indicator diagram beta?
PV diagram.
PV diagram, right? So on PV diagram, what is going to be slope of the polytropic process? Okay beta? Like what we know that PV to the power x is equal to constant. I want to find out slope. So say that constant is some C. Okay? Now what I want? dP by dV I want. dP by dV I want. So I can write P is equal to some constant V to the power minus x. So then dP by dV is equal to C into minus x V to the power minus x plus 1. Right? Now this C was a constant. So means PV to the power x a constant. So individually P can change, individually V can change, but this whole thing will remain same. So even your volume is changing, right? But this constant I can put PV to the power x of any instant. Yes.
So it should be V raised to minus x minus 1.
Minus 1. Oh yes, thank you. So minus x minus 1. Okay. Now minus x, C should be PV to the power x, V to the power minus x minus 1. So what I am getting beta? Minus x into P by V. Right? So that is what? Slope on indicator diagram, a formula. For example, very common example is, sometimes two graphs are shown to you. PV on PV indicator diagram, two graphs are shown to you and they are asking, out of these two graphs, one is isothermal, one is adiabatic. Do you remember this question? Okay, say that upper one, this is A, that is B. Out of A and B, one is adiabatic and other is isothermal. So can you say that which one is adiabatic or which one is isothermal? A is and B is why?
Slow.
Yes, because if you see slope dP by dV, slope on isothermal, for isothermal process, slope will be, now x is what? 1. PV to the power 1 constant for isothermal. So x is 1. So what I will get? Minus P by V. Okay. And for adiabatic process, slope is what, beta?
Gamma P by.
Minus gamma P by V. Gamma is a Cp by Cv. We know value of gamma is always greater than 1. Right? Okay. So now, at what 2 points you are comparing slope? Some students are saying slope of adiabatic is more in comparison to isothermal. At intersection point, obviously, right? So when values of P and V are same, at that point only we can compare. If two separate graphs are given without any intersection point, then we cannot directly say, we don't know, right? But here, since some intersection point is there, I can say just by looking at the graph, I can say P and V are same. So more gamma value is more than 1. So more is the slope, right? A graph having more slope should be what? Adiabatic. So this graph has to be what? Adiabatic, A. So A is adiabatic and B is isothermal. So like that, we can compare any two polytropic process. We can identify, right? From the point of intersection by the use of slope, we can identify the type of process very easily. Yes, but understood or not? Okay. So that is property number 1, slope on indicator diagram. Now property number 2. Property number 2, bulk modulus. Okay. Bulk modulus. Now what is the formula of bulk modulus, bete?
Delta P by delta V by V.
Minus delta P upon delta V by V. Right? So for small changes I can write minus dP by dV into V. Yes or no? So if you remember in the derivation of velocity of sound, I said what is bulk modulus of isothermal process, what is bulk modulus of adiabatic process. Remember beta? Yes. Now dP by dV is what beta? Minus x into P by V. Right? So minus minus plus. So what it will be now? X into P. So if you substitute dP by dV value here, minus x into P by V. So minus x into P by V into V. V cancel. What you are getting? Just x into P. For isothermal process, x is 1. So bulk modulus of isothermal process is what? Just pressure. So if for an isothermal process bulk modulus is given, it means indirectly what they are giving? Pressure. For adiabatic process, bulk modulus is what? Gamma into P. Like that. Okay, beta? Slope, bulk modulus. What will be specific here? That I already told, right? Okay. Number 3. Work done by gas you can obtain indirectly, but directly also by the use of formula you can get, right? Work done by gas. Work done by gas. Now work done by gas will be what beta? Q minus delta U. Yes or no? So Q is what? N C delta T or dt. Right beta? And du is what? N into Cv into dt. Yes or no? Okay. Now specific heat formula you already know. So what is specific heat formula beta?
Cv plus P by N.
Cv plus R
by 1 minus X.
1 minus X minus Cv. See, a beautiful formula is coming. So that is nR dt upon 1 minus X. So here, say small work done I am writing first. And now since everything is constant, nothing is variable, directly I can write work done by gas is nR delta T upon 1 minus X. So it doesn't matter what is the type of process. If work done by gas is required, directly we can put value of X here. The question that you just solved, you first calculated the heat and then internal energy and then you are subtracting it. So that is work done by gas, directly you can get. Okay, bete? Okay. Now what about isothermal process? If a process is isothermal, X is 1. So if you put X is equal to 1 here, work done by gas is coming what? Infinity? No, 0 by 0 form, beta, which is not defined. Okay. Now it's not an exceptional case. Right? I can say that it is an exceptional case. No, it's nothing like that. It is just like mathematically this equation is not valid. Some equations mathematically are not valid. It means what we need to do? We need to solve it by some other method, because mathematically this equation is not correct. 0 by 0 form. Then how we can find out work done by gas then? Work done by gas for any process, general formula you know, it is what? Integration of T dV, right? It means work done by gas I need to find out by this method, right? I need to find it by this method. So I can write, now P is what? nRT by V into dV for isothermal. So if process is isothermal, so what I can do, beta? nRT I can take out 1 by V into dV. So then work done by isothermal process is nRT ln V2 by V1. Okay? This equation, or you can also write nRT ln P1 by P2. Okay? So like this. So that are some of the properties of. So that is property number 4. So how we can obtain it, right? So in thermal physics we have covered this formula. Delta V is equal to V gamma delta T. But this gamma is different. That is coefficient of volumetric expansion, right, beta? For gases, for small changes, what I can write, beta? Gamma V is equal to 1 by V into dV by dt. I can write like this. Yes or not? Right? Okay, so that is the origin that you must know, that you must remember, that what is coefficient of volumetric expansion in gases. Now, see, PV to the power x is equal to constant, that is our polytropic equation, right? I can rearrange this. So what I can do, beta, because I want the expression of volume in terms of temperature. So what to do? P I can write what? nRT by V into V to the power x is equal to constant, right? Okay, so I can write what? V to the power x minus 1 is equal to T to the power minus 1, yes? Into some constant. V to the power x minus 1, T to the power minus 1 is equal to constant. So means I can write V is equal to T to the power 1 upon 1 minus x into some constant, yes or no? Clear? Okay, because I want to obtain dV by dt, this term I want to obtain, right? So dV by dt, so now this will be 1 upon 1 minus x T to the power 1 upon 1 minus x minus 1. So this will be what, beta?
X by 1 minus
T to the power x upon 1 minus x, right? Okay. Yes, beta?
so constant.
Constant, right? Into some constant, right? Okay. So I want to obtain dV by dt. So if you see what are those constants, right? So each and every constant we need to find here, because we need to substitute here, right? So 1 by V into 1 upon 1 minus x T upon x upon 1 minus x into C2, right? Okay. Now what is the value of C2? Just rearrange it and tell me what is going to be the final answer. Yes. So mathematically just solve it. Okay. Mathematically just solve it and tell. So as we have obtained the constant C2, Mr. Ayush has obtained this constant C2 as T to the power 1 upon x minus 1 into V, and after simplifying it, what we are getting? The expression of gamma V, coefficient of volumetric expansion, right? So that is the fourth property Okay, that is the fourth property of polytropic.